Welcome to the Chemistry 1406 test review number 2. I've shared our very large test review into the chat. It's a practice test with about 100 questions, if not more. We won't be able to get to all of it, but we will try to get to especially those questions that you feel would be most helpful to you. So what I'd like you to go ahead and do is take a look over it, and once you find certain questions that you'd like to go over, one of our attendees said, I'd like to practice a few problems like 23. Just watch someone work through this sort of equation another time. Okay, so let's take a look. Look at 23, then jump into that. It says, and I'll zoom in a little bit. You may have to zoom in yourself to see it more clearly. And I apologize for those of you watching the video because this is going to be a little bit harder for you to see. But it says, how many molecules of TNT, C7H5N3O6 are in 5.8 moles of TNT? So I think the key thing is it says molecules here, and we're given moles here. To go from moles to molecules, what do we need to do? To go from moles to molecules, what do we need to do? Avogadro's number, very good. So what we'll do is we're going to start with our given amount, 5.8 moles of TNT. And then we'll multiply, forgive me, we'll multiply times the conversion factor. Now moles of TNT was previously on top, so it has to come on bottom so it cancels out. And then 1 mole of TNT is equal to 6.022 times 10 to the 23rd molecule. And that's pretty much it. It's a one-step conversion in this case, so it's actually not as challenging as you might expect. So in this case, if I do that, I should get 3.5 times 10 to the 24th. What question would you like to hit next? Yeah. Yeah, and that's completely understandable. Basically, a lot of times, problems will sometimes give you extra information that you don't need, and that can definitely throw you off. So, any other questions you'd like to go through that you know offhand? Should we go back to the beginning? What do you think?
I think we should go back to the beginning. For me, it's a balancing of equations. I don't really know how to. The balancing, the one that has to do with you putting numbers in front of the equation or something.
Sure.
Like number 2, something like that.
All right. So, should we maybe tackle problem number 2? What do you think?
Yeah.
Please, let's start from number 1. For us who didn't do it before.
We can go with, yeah, sure, we can go with number 1. So predict the missing product of the following unbalanced equation. Well, for something like this, you see that magnesium is being combined with nitrogen. First thing you want to do is identify, is magnesium a metal or non-metal? Hmm. A metal. And is nitrogen a metal or a nonmetal? Hmm. So you have a metal and a nonmetal. If you have a metal and a nonmetal, then that means that this is going to be what type of compound in the product that combine a metal and a nonmetal. Ionic, very good, very good. So since it's ionic, what I have to do is I have to figure out what the charges are going to be. What charge does magnesium tend to have? If you look at the periodic table, what charge does magnesium have? 2 plus. And what charge does nitrogen have?
Minus.
Or the nitride ion? Yeah, 3 minus. So magnesium's a 2 plus, nitrogen's a 3 minus. So the lowest common multiple of 2 and 3 is 6. So how many magnesiums do we need to get a total positive charge of 6? 3. Very good. And how many nitrogens do we need to get a total negative charge of 6? Mm-hmm. So the answer here would be magnesium nitride Mg3N2, or D. Does that make sense? Cool. Now we can take a look at question number 2. It says, which reaction below gives a balanced equation such that the sum of the coefficients equals 10? So this is a really challenging one because you have to balance all these equations and then figure out which one has a sum of coefficients equaling 10. The first thing that I'd like to have you keep in mind is you want to balance it element by element, and you want to balance whatever is easiest to balance first. And the easiest elements to balance are those that appear in the fewest compounds. So for A, I see I have HCl, CRS, CrCl2, and H2. Sorry, it's not CRS, it's just chromium solid. So each of these, the hydrogen appears in 2 places, the chlorine appears in 2 places, and the chromium appears in 2 places. So each of these um, are equally easy to balance, and it doesn't really matter which one I balance first. So I can go ahead and balance this. I can be like, okay, well, let's balance, I guess, chlorine, because chromium's already balanced. Let's balance chlorine. There are 3 chlorines on the right side, so that means I'm going to have to put a 3 in front of HCl here. Now there are 3 chlorines on the left side as well. Chromium's balanced, chlorine's balanced. Now I can balance hydrogen. But here we run into a little problem. Hydrogen has a coefficient of 2. Or rather, there's 2 hydrogens on the right-hand side. It's H2. I have an odd number that I'm trying to balance with an even number, the 3 H's on the other side. I can't use like 1.5, so whenever you're trying to balance an odd number with an even number, you typically want to double the odd to make it even. So which side has an odd number of hydrogens? The reactant side or the product side? Which side has an odd number of hydrogens right now? No, actually, the product has an even number. The product has 2. It's the reactant side that has the 3, that odd number of hydrogen. So I have to double the odd. I have to double that 3 into a 6. I now have 6 HCl. Well, now I can balance the hydrogens on the other side. If I have 6 hydrogens on the reactant side, I can put a 3 in front of H2O, or rather H2 rather. But unfortunately, if I do that, I also have to balance the chlorines, which are now 6 on the left side, 3 on the right. So I'm going to need 2 chromium chlorides. which means I now need to rebalance chromium. So I put a 2 here. At this point, if I add up the coefficients, this is clearly not going to give me 10. This actually gives me 13. So A is not the answer. I was actually just thinking about this, and I'm going to go ahead. I want you all to be able to see this better, and I also want to be able to work this out in a way that is easier for you to see. So in that case, let me ask you a quick question. Was it a little bit hard to follow without me listing the elements? Would you prefer that I listed the elements? Okay, yeah. All right, so I'll go ahead and I'm going to pull this up here. Give me just one moment. And I'm going to pull up the Word file. This should be easier for you to see and follow. Everybody see that? We good? Cool. All right, so we've already balanced this. It was a 6, a 2, a 2, and a 3. That's not our answer. Let's go ahead and balance some of these other ones. All right, for this next one, I have several different elements. I'm going to go ahead and list out my elements on each side. I have Fe, Cl, I have Na, I have carbon, and I have oxygen. I'm going to list out the same elements in the same order so I can keep track of them more easily. Fe, Cl, Na, C, and O. Now there are some who will say, well, you can keep polyatomic ions together, and that's sometimes true and it's sometimes not true. For me, I actually don't find that it saves you any time, really, to keep them together, and I find it in more cases it actually leads students to have greater confusion about what's going on. So I am not a big fan of doing that. I'm just going to go ahead and separate each element. We'll balance it element by element. So how many irons do we have on the left side? Uh-huh. And how many chlorines do we have on the left side?
3.
Mm-hmm. How many nitrogens do we have on the left side?
1. Sodium, you mean?
Or sodium, rather, not
2.
nitrogen.
2.
Sodium. And how many carbons?
1.
One. And how many oxygens?
3.
Yeah, you guys got this. You're good at identifying this. 2, 1, and 3. And on the product side, you'll see we have 2 irons, 1 chlorine, 1 sodium. How many carbons?
3.
3, very good. And how many oxygens?
9.
9, very good. All right, so I want to balance whatever is easiest to balance first. It turns out that each one of these is equally easy to balance because if we're looking at the different substances, iron only appears in 2 places, chlorine only appears in 2 substances, sodium only appears in 2 substances, carbon only appears in 2 substances, and oxygen only appears in 2 substances. So because in this case, it doesn't matter what I balance first. I can go ahead and just go top to bottom. Okay, so I'll balance iron. I got 2 irons on the product side, 1 on the reactant side. What do I need to do?
Balance the one on the left, on the reactant
Can't
side.
quite hear you. I don't know if you can speak up or get closer to the microphone.
Balance the one on the reactant side. Make that
How?
2. It's 1, right?
So what do I have to? What coefficient do I have to put in front of what compound?
In front of iron, you put 2.
2 in front of FeCl3, right?
Yeah.
So that's going to give us, that's going to multiply times the Fe, it's going to multiply times the chlorine. So it's 2 ions, and that gives us 6 chlorines, right? All right. So now, next we're going to go ahead and balance the chlorine. So what do I have to do to balance that? What do I have to do to balance that? Yep, very good, Leanne. 6 NaCl's. I put a 6 in front of NaCl. On the product side, that's going to give me 6 NAs, and it's going to give me 6 Cl's. Now I can balance sodium. I have 2 on the left side, 3 on the right. What do I have to do there?
You add 3 to the Na. Oh no, that's
Yeah,
what
3.
3.
Yeah, 3 to the Na2Cl, or CO3 rather, right?
Mm-hmm.
That gives us 6 NAs. How many carbons does that give us?
9. No, 3.
3. And how many oxygens?
It's gonna give you 9.
So now I see that balancing the first 3 elements actually took care of the last 2, so I don't have to worry about it. It's going to just be a 2, a 3, a 1, and a 6. Now, do those coefficients add up to 10?
More than 10.
No, that's more than 10, right? 7 on the product side, 5 on the reactant side, so that'll be 12. So that's not our answer either. So let's go ahead and look at the next one. I'll go ahead. What did I do? There we go. All right. So now we just go ahead and we list our variables, list our elements again. Pb, F, H, and O. On the product side, likewise, Pb, F, H, and O. Once again, I'm going to balance them one by one. So this is one where you could not keep the polyatomic ions together even if you wanted to. So once again, like I said, it doesn't really help you to keep the polyatomic ions together or to try to. I find that in most cases it just ends up bringing greater confusion. But I am going to go ahead and balance whatever is easiest to balance first. In how many compounds does lead appear?
1 1. Lead is 1 1 on both
One
sides.
on the product side, one on the reactant side. So a total of 2, right?
That 2 is 1 1.
Uh-huh. So 2. How many compounds does sulfur appear in?
Sulfur is 2.
Also 2, the PbS and the PbSO4. What about hydrogen?
Hydrogen is
Yep, also 2. And what about oxygen?
okay, 2, sorry. Oxygen is 2.
No?
On both, are you doing on both sides or only one
On
side?
both sides. Yeah,
Both
on both
sides.
sides. Yeah, oxygen appears in
3.
3 places. So oxygen is definitely going to be, um, no, we're not counting total, we're not
Sulfur
counting
is
total
7 now.
oxygen. We're
7.
only counting the amount, the number of different substances that oxygen appears in. That's why I used a different color. I didn't use the blue color I usually use when listing the elements. Yeah, these are just indicating how many places they appear.
Okay.
So it looks like oxygen, which appears in the most places, is going to be the hardest to balance. I'm going to wait till last to balance it. Now I'm going to list out my number of elements of each type on each side. On the left side I have 1 lead, 1 sulfur, 2 hydrogens, 2 oxygens. Pretty straightforward. On the right side I have 1 lead, 1 sulfur, 2 hydrogens, and how many oxygens?
5.
Yeah,
5.
5. Very good. So now I look at these and I went, okay, well, the only thing I have to balance is the oxygens. That's a little awkward. So I'm going to go ahead and double the odd to make it even. So the only way I can balance the oxygens is I can double the odd to make it even. So I'll double the odd, in this case the hydrogen,
Five.
and I'll make it 2.
Two.
And if I do that, that odd number of oxygens now becomes 6 because there's 2 from the water, 4 from the lead sulfate. But I now have 4 hydrogens. I need to go back and balance the easier one, the hydrogen. So I have 4 hydrogens on the right side, 2 on the left side. So I will put a what in front of H2O2?
Two.
Yeah, 2, right? That's going to give me 4 of these and 4 of these. Well, that's still not quite enough. So I'm going to have to continue to increase it. If I want more oxygen, I'll probably have to go back and forth a little bit here. I'll change this 2 to a 3 in order to balance the oxygen. That gives me 6 of these and 6 of these. But the problem is, once again, the hydrogen. Um, so I'm going to have to change this 2 to a 3 to get this hydrogen up to 6.
Six.
But now I have an odd number of oxygens again at 7.
Mm.
And as you can see, this may go on for a while. And this is one of those cases where back and forth, it's kind of it can get a little confusing, and it can start to be a little bit annoying and frustrating. Start ramping it up too far, so to speak. But one of the things I think to notice here is that there's an oxygen deficit. That this has the same number of hydrogens in this compound on the left as it does on the right, but this one has 2 oxygens for every 1 here. I have to make up for 4 oxygens. So if you recognize that, you can end up actually just changing this to a 4 here to give me 4 or 8 hydrogens and 8 oxygens. And on the other side, change this to a 4, and that will give you 8 hydrogens and 8 oxygens. And one thing you can also see is by looking at the pattern on the right side, I started out with 2 hydrogens and 5 oxygens, but then as I continued to add more water, that deficit grew smaller. The 2 hydrogens, 5 oxygens, 4 hydrogens, 6, now it's a difference of 2, 6 hydrogens, 7, now it's a difference of 1. I just needed to give it 1 more water, and that changed the deficit, or that was even. It's 8 to 8. Now, admittedly, if you come across a problem like this, it can be fairly complicated to balance. A professor probably will not give you one like this, but there's another way to balance these harder equations using algebra, but unless you're very mathematically inclined, uh, it might just end up being more confusing to you. If you want, I
Professor,
can show you the algebraic way of solving it. Would you like to see it, or do you think that would just be a waste of time?
would love to see it.
I can't hear you. Sorry.
I say would love to see it. You said Professor something. Our lecturer is not a professor. She's a doctor. What's her name? She's a lady.
Parish.
Yeah, Dr. Parrish.
Yeah. So basically, I'll go ahead and just put the 4 and the 4, and that would be balanced. So another way you could balance this is by, instead of doing what I did here, and I'm actually just going to quick erase this all. Instead of doing everything that I did here, you can actually set up equations for each element. And the equations are actually really easy to solve if you know how to once you get it started. But basically, I put a coefficient in front of each of these. So I say a, this will be little a, little b, little c, and little d. These are 4 variables. So now I'm going to make an equation for each one of these. I know that the amount of lead has to be equal on the product side to the amount of lead on the reactant side, right? In PBS, there's only one lead, isn't there? So I can say 1 times the letter A is equal to the number of lead on the reactant side. So you have the reactant side and you have your product side. So 1A, or just A, is equal to the amount of lead on the reactant side. And that's equal to 1 times C, because C is the compound that has, the C compound is the one with the lead on the product side, and there's only one lead there, so A is equal to C. So those coefficients are the same, and that's my equation for lead. So then I do an equation for sulfur, and for sulfur, I see once again, there's 1 sulfur in PBS, so the coefficient of PBS is A, so A times 1, or 1A, or just A, is equal to, on the product side, the sulfurs in PbSO4, and so there's only 1 sulfur there, so it's 1 times C, or just C. So notice it ends up being the same equation for Pb and S. Then I do an equation for hydrogen. Or not H2, but just hydrogen. So for hydrogen, on the reactant side, the hydrogen is in the compound H2O2, and the coefficient of that compound is B. Since there are 2 hydrogens in that compound, I'll say the total number of hydrogens on the reactant side is 2 times the coefficient, 2 times B. On the product side, the hydrogens are in H2O, and there are 2 hydrogens in H2O, so that's 2 times D hydrogens on the product side. And of course, that can be reduced to simply B is equal to D. So 2B is equal to 2D, or B is equal to D. So now I have oxygen. Oxygen, on the reactant side, all the oxygen is in H2O2. There are 2 oxygens, so it's 2B. And on the product side, there are 4 oxygens in PbSO4, so it's 4 times C. And there is 1 oxygen in water, so it's plus D, plus 1D. So here are my equations. A equals C and B is equal to D. And 2B is equal to 4C plus D. Okay, so what I can do here is I can say, well, I know that D has to be equal to B. And I know that um, yeah, so 2b is equal to 4c plus d. Oh, did I make a mistake here? No, that's right. B is equal to D. And 2 times D for the oxygen. And okay, so what I can do here is I can say, okay, well, I know that, well, shoot, does this actually work?
I think this one is more confusing. I'd like the one about working with the numbers. The first
Yeah,
one.
yeah, exactly. No, this is a really tricky problem because of the way that it's set up. And I think that this would work, but you would basically what you have to do is you have to substitute. You have to substitute B in for D and be like, okay, well this is oh no, actually this works. This does work. Okay, so what you do is you just look at this and say, okay, well B is equal to D. So I'll just substitute the B in for D, and so I get 2B is equal to 4C plus B. There's 4C plus D, but since B is equal to D, I substituted B in for D. Then I can subtract B from both sides, and that gives you B is equal to 4C. So now, if you assume that the lowest, so if you assume one, you then have to assume one of your values is equal to 1. Okay, so in this case, I might assume that, like, for example, the coefficient A is equal to 1. So if A is 1, if A is equal to 1, then what's B? Well, first of all, I can say if A is equal to 1, then C is also equal to 1 because A is equal to C. And then if C is equal to 1, B is equal to 4C, so B is equal to 4 times 1, so B is equal to 4. And since B is equal to D, then that means D is also equal to 4. And so I get 1, 1, 4, 4, which is what it actually is. So yeah, that algebraic method, if that doesn't work for you, totally cool. Don't use it.
No,
Because it is, like I
I
said,
like
it
what
is
you
a little
brought.
bit math heavy and it is a little bit complex.
It's
But maybe I thought it would help. I don't know.
because the one you're working with the numbers, you're just seeing the numbers there. So if they are not adding up, you know they are not adding up. You increase or you decrease.
Yeah.
It's workable than this one. This one I don't like what you brought on.
Yeah. Did anybody understand my little algebraic method?
I don't think
Uh,
so.
Yes.
okay. So I don't know if it was helpful at all, but maybe it wasn't. So I apologize if that was a waste of time. Um, but that yeah, that's another way to do it. But like I said, I usually don't use the algebraic method because usually, like I said, it takes the only time it's really worthwhile is when you have a really complicated equation that doing it the other way is just obscenely hard. But otherwise, this just gets too complicated, and for most students, it doesn't really work. Well, it looks like our answer definitely then is C, because these coefficients most certainly do add up to 10. Do you want to balance D?
Did you say everything you did just balanced to 10 just now?
Yeah, because the sum of the coefficients is equal to 10, right? 1, 1, 4, and 4.
No, okay. No, without using this one, when we worked it, when we did it the other way, was it 4? Was it also 10?
Yeah, it was a 4 in front of the PBS, or 1 in front of PBS, and then a 4 in front of H2O2, a 1 in front of PBSO4, and a 4 in front of water.
Okay, that should be our
So
answer then. So,
so basically, In both ways, we got the same answer. It was a 1, a 4, a 1, and a 4. And that those coefficients do add up to 10. So this is the correct answer. That one has a sum of coefficients equaling 10. Kind of an evil problem, I'm not going to lie. Probably won't get anything quite that hard. Okay. Do you want to balance the D just for the heck of it? No, no, don't balance D. Okay. All right. So in that case, let's go. No, question number 3 basically says which equation below violates the law of conservation of mass. Well, the law that basically means which equation is not balanced. That's basically what it means. Which equation is not balanced? And so if you look at these, this is a little bit easier because you don't actually have to balance the equation. You just have to identify which one is not balanced. So is the equation A balanced?
No.
No. There's 2 carbons on the left side, but there's 4 carbons on the right side. So that is not a balanced equation. What about equation B? Is that balanced? Well,
Yes.
no, actually, equation B is balanced. It's not
Balance.
correctly balanced in the sense that it is, in that you would always want to use the lowest whole number ratio, so it should be 2, 1, and 2. But it is technically speaking not violating the law of conservation of mass because there's equal number of atoms of each type on both sides. Um, what's wrong with equation C? Which element is not balanced there? Yeah, the hydrogen. There's 3 hydrogens on the left side, but only 2 on the right side. And what about equation D? What's the problem there?
D is balanced.
The D technically is balanced, but it's not actually an equation, right? The products and the reactants are the same thing.
Yeah.
So in this case, there are 2 equations that violate the law of conservation of mass. There's A and there's C. I think the original, because I got these questions from somewhere, whoever wrote the original questions probably made the mistake of not writing the formula properly for C, but there's actually 2 equations that violate the law of conservation of mass. So I'll highlight those 2 here.
What is the law of conservation of mass? What's that?
It just basically states that the mass you start with is the mass you end with. In other words, the the number of elements on the left side has to equal the number of elements on the right side of each type. So this one violates the law of conservation of mass. It could be that, yeah, so it could be that there's something else going on there, but yeah, that violates the law of conservation of mass, and this one violates the law of conservation of mass. So there's actually 2 answers here. All right, cool. This is another sum of coefficients equation. Do you want to skip that one and maybe look at some other problems?
No.
What do you think?
I think we should do it.
Let's do that. Okay, so it's in number 5. Okay, let's do number 5. So it says in a combustion reaction, which of the following is not a product?
Energy.
What do you think?
Energy is not a product.
Actually, that's not true. If you burn something, doesn't that release energy? Light
Mm,
energy, heat energy?
so,
And not all of them are products. All of them are involved in a combustion reaction, but which one is
okay.
not a product? Which one is a reactant?
Oxygen.
Oxygen. That's right. So that's the tricky one. That's one you got to kind of think about for a second. Yeah. Oxygen's a reactant, not a product. Cool. Now the next one. What is the sum of the coefficients on H2O and H3PO3 when this equation is balanced? You want to try this one? All right, let's go ahead and hit this one. This will give you more balancing practice. Do you want to take a stab at it on your own, or do you want to work it together? Um, what do you think? I can give you a minute or two to work on it on your own. We can go over it together, or I can just go over it together with you right now. Okay, let's try it on your own. So use the same skills that we used in balancing it before, but now try it on your own. And this will be a good opportunity for you to practice and make sure that you understand it. So let's go ahead and give this a shot. Once you have the answer, go ahead and hit your raise hand button. You can click on your little guy there down by your audio. All right, we got one person ready. Yvonne, you're not supposed to give the answer. You're supposed to let us know you're ready. You got two people ready. You can also feel free to raise your hand if you give up or if you just want to go ahead and start working on it all together. Okay, let's go ahead and dive into this. Krista, since you were the first one to raise your hand, would you like to go ahead and walk us through the process?
Okay.
You don't have to
So
if you don't
on
want.
the left side, I will. So the left side, I have uh, P is 1,
Okay.
CL is 3,
Mm-hmm.
H was 2, but I moved it to 6.
Uh-huh.
The other side, P is 1, CL was 1, H was 4, and O was 3.
Uh-huh. Okay. And so what did you choose to balance first?
I balance the chlorine first
Okay.
on the right side.
Okay. So you put a 3 in front of this,
Yep,
and that made this 3, and it made the hydrogens.
a 6.
Yep. Good.
And then went over to the other side and I put a 3 right there.
Uh-huh.
And then made we had
6 and
that a
3.
6 and that a 3.
And then it was balanced. Yay, very good. Yeah, it's a 1, 3, 1, 3. Did anybody else get that?
That's what I have.
Awesome. Good job, Yvonne. Rock on.
So when I asked the question, what is the sum of the coefficient of those two, you just add 3 and 1 and it's 4?
Exactly. So the answer
Okay.
for this problem would be 4. Very good.
Okay.
All right. So have you had enough balancing, or you want to try something else? What do you think?
I think
I
we
think
should do
something else.
balance.
Try something else? Okay. So we've gone over some of that. So we have limited time. So definitely want to make sure we cover some other things. What would you like to what would you like to dig into next? So maybe look at types of reactions. Maybe. What do you think? 11? Sure. All right. So it says when electric currents pass through water, this equation this occurs. What type of equation is this? When you have one reactant and it breaks down into,
Decomposition.
well, yeah, decomposition. One reactant breaking down into multiple products, that's going to be a decomposition. Very good. All right. So let's keep going. Did you guys do anything with oxidation and reduction? Do you have to know anything about that? What do you think? Did you learn anything about oxidation and reduction?
I feel like we did, but I don't remember.
Okay. Well, I'll show you the easy way to do oxidation and reduction. So let's take a look at this. So it says what is oxidized and what is reduced in the following reaction. So first of all, we have to understand oxidation um, is an increase in charge. Yeah, so let's see. Oxidation as far as you're concerned, I mean, technically speaking, there is a more um, specific, there's other definitions that you can use, but I find like this is the most useful. Oxidation is an increase in charge, an increase in charge. In other words, the charge becomes more positive or less negative. And reduction, conversely, is a decrease in charge. See, whenever you've heard the word reduction in your life, has it referred to an increase or a decrease?
Decrease?
Decrease, yeah. If they said, we're reducing your pay, there's going to be a reduction in your pay, you'd be like, oh no, I'm losing money, right? If there's a reduction in the workforce, that means there's fewer people working. So reduction is a decrease. And the reason it's called reduction in this case is because it's a decrease in the charge or oxidation number. Now, oxidation number and charge are not synonymous. In other words, they're not exactly the same thing, but they're close enough to the same thing for your purposes. So if I'm looking at these elements, the aluminum and the bromine, when an element is by itself in the elemental state, its oxidation, its charge, does it have a charge? Do you see this aluminum having a charge right now? Actually, no. In its elemental state, it doesn't have a charge. If it's by itself and you don't see a charge, that means there's no charge. So yeah, there's no charge here. So as a result, you could say the charge of this is 0. Likewise with bromine. Bromine's in its elemental state. Is there a charge there? Do you see a charge? What's the charge of bromine in Br2?
Too close.
Yeah, it's 0. There's no charge there because it's by itself. Any element by itself in its elemental state has 0 charge, no charge. Now on the other hand, on this side, you have aluminum bromide. So this is what type of compound? Aluminum's a metal, bromine's a non-metal. What type of compound is this?
Ionic.
It's ionic, exactly. So since it's ionic, that means they do have charges. What's the charge of aluminum in aluminum bromide?
Three.
What's that again? Yeah, 3 plus. What's the charge of bromine or bromide in aluminum bromide? Yep, very
Minus.
good. 1 minus. So aluminum goes from 0 to 3 plus. Is it oxidized or reduced?
Oxidized.
Would you say?
Oxidized.
Oxidized. Very good. Yeah, it was the charge increased, so it's oxidized. And therefore bromine, which went from 0 to -1, that's what?
That's reduced.
That's reduced. So the aluminum is oxidized and the bromine is reduced. And so the correct answer to this question is A. An oxidation reduction reaction is any reaction where the charges are changing. Any reaction where the charges are changing, where the oxidation numbers are changing. All right, cool. So note one very important thing here, and I'm going to write this down because it is so important. Only only reactants, only reactants can be considered to have been oxidized or reduced. So only reactants can be oxidized or reduced. Products cannot be oxidized or reduced. Products cannot be oxidized or reduced. Only reactants can be oxidized or reduced. So therefore, the products are simply the result of oxidation and reduction. So if you look at question number 3, or answer choice B, that's automatically invalid because aluminum bromide can't be oxidized or reduced. It's a product. Likewise, answers D and E are also invalid because aluminum bromide, like if once again, it's a product, it can't be oxidized or reduced. So that only leaves you with A and C. At least that, then it's a coin flip. But if you understand how to figure out the charges, you can see clearly which one's an increase in charge and which one's a decrease in charge. Unfortunately, they oftentimes will give an alternate definition of oxidation, which they might ask you on a test. And that basically, well, oxidation, there is an increase in charge, but it increases its charge because it's a loss of electrons. By losing electrons, oxidation is an increase in charge. And reduction has a decrease in charge by gaining electrons because electrons are negative. So reduction is sometimes also referred to as a gain of electrons. Sorry. And this leads to several of the silly acronyms like oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. You might have seen this. Reduction is gain. Oxidation is loss. But the only reason I don't like that is because it's not reduction. When has reduction ever been a gain? The word reduction does not mean gain. It means a decrease. So the reason why it's called reduction is not because you gain electrons. The reason why you call it reduction is because you decrease the charge. And in the context of trying to figure out what's oxidized or reduced, it makes more sense to think of oxidation as an increase in charge and reduction as a decrease in charge. I hope that helps. Any questions on that? All right, cool. So let's go ahead and move on. Any other questions you want to go ahead and take a look at? What do you want to hit? You want to do any formula weight stuff, or do you know how to do the molar masses okay? What do you think? Number 15? Okay. So what is the formula weight of beryllium sulfate? Well, first we actually have to write the formula for beryllium sulfate. So what is beryllium? What is beryllium? Anybody know what this? It is an earth metal. Yeah. And what is the formula for it? The chemical symbol for beryllium. Yep. So it's Be. And what charge would it have? Since it's a metal, and we pretty much know that metals are going to be part of ionic compounds, because covalent compounds are just nonmetals, two nonmetals, but ionic compounds always have a metal. All right, so I have beryllium, and then what's sulfate? What's sulfate? That's nitrate. What's sulfate? Anybody remember? There you go. Yeah, this is one of those polyatomic ions that you're supposed to have memorized, which you may not already have memorized, in which case, that's bad. No. You still have time to memorize it. You're okay. So you have beryllium and you have sulfate. Here's beryllium, here's sulfate. They have equal charges, so the formula is just going to be one of each, BeSO4. So now you just calculate the molar mass by adding up the masses of each element. So beryllium, there's one element of beryllium, and that's one of the few that I don't have memorized off the top of my head. What is the mass of beryllium? Uh, very good, 9.012. All right, sorry, my bad. All right, so it's 9.012. And then we have sulfur. Sulfur, there's one sulfur. It's 32.065 or 32.07 roughly. And then there's oxygen. There's oxygen. 16.00. So of course, obviously 1 times 9.012 is 9.012. Sulfur is 1 times 32.07. And oxygen is 4 times 16, which is going to give you 64. And then you go ahead and add those up. So um, this basically gives you roughly about 0.08 and then 105. So 105.08 if you add those up. In this case, the closest one is 105.0. Does that make sense?
Yeah. So the most important thing is for you to be able to know the formula, and then for you to be able to
Yeah.
work it.
Once you know the formula, yeah, everything else just kind of falls into place. Hmm. All right. So, what do you want, what problem do you want to look at next? You feel like you got more math? You want to just what do you want to take a look at next? Do you think?
Everything looks difficult. I'm
Okay, so
sorry.
it says I can convert molecules to grams. Would that be helpful? Yeah. Okay. So it says what is the mass of a thimble of water, which contains 4.0 times 10 to the 21st molecules of water? Um, so what I would go ahead and start with here is what I'm given, of course. It's 4.0 times 10 to the 21st molecules. And this is molecules of water specifically, H2O. So I can't convert molecules to grams directly, right? What can I convert molecules to?
Mole.
Yeah, moles. I'll convert molecules to moles. Molecules comes on the bottom, moles comes on top. Now, what numbers do I put on top and bottom? What goes in front of molecules?
6.022.
What number goes in front of molecules?
6.022.
Sorry, I couldn't quite hear you. Yeah,
6.022
yeah, not just 6.022,
times
6.0222 times what?
1023.
Times 10 to
1023.
the 23rd, yep. And that's going to be equal to what number on top? How many moles?
1.
Yeah, just one, right? So that converts my moles to molecules to moles. But once I have that, then I still have to convert the moles because I need the mass. The moles is going to go on the bottom, cancel. And what's the unit of mass?
Gram.
Grams. So in this case, I have to convert moles to grams, which means I need the molar mass. And what's the molar mass of water?
H2O. 1.008 plus
No?
times 2 plus
Oh, there you go. 18.016. That's right. 18.02. Thank you, Brittany. 18.02 grams is equal to 1 mole. So then I go ahead and I divide the bottom and multiply by the top. And if I do that, what do I get?
26,263 points. I'm not sure if that's correct. It's not correct.
No, not quite. No, Brittany has it, but she has it in really weird notation. I think you have your calculator set to like engineering notation or something. But yeah, yeah, basically 0.12. Yeah, it ends up being 0.12. So you have to be careful about how you put this in the calculator. If you use the E button, like 4.0 E21, don't do 4.0 times 10 E21 or you'll get the wrong answer. Um, so yeah, if you're going to use that EE button on the calculator, it's 4.0 E21 divided by 6.022 E23, and then you multiply times 18.02. All right, cool. Very good. Now, let's see. We already did 23. What do you think? Should we? How about something like this? What do you think? One where we actually have to do conversions, a little stoichiometry. Should we jump into 27 maybe? All right. So it says how many grams of nitrogen will be required to completely react with 9.3 grams of hydrogen. So in this case, it already gives you a balanced chemical equation. So you do not have to worry about balancing the chemical equation. All you have to do is 9.3 grams of hydrogen. So the grams of hydrogen needs to be converted into grams of nitrogen. But we can't do that directly because the only way to convert from one substance to a different substance is with a mole-to-mole ratio. So grams of hydrogen is going to have to come on bottom, but what can I convert grams of hydrogen to? Yeah, moles, exactly. Moles of hydrogen, right? Can only convert grams of hydrogen to moles of the same thing. So 1 mole of hydrogen, and hydrogen is 2 of them, so it's 2.02 grams is equal to 1 mole. Now that I have moles of hydrogen, I can convert to moles of something else. So moles of hydrogen is going to go on the bottom. What's going to go on top? Moles of N2, yeah. Moles of what I'm looking for. And what's the ratio? What numbers go in front of N2 and H2? Where do I find those numbers?
Periodic table.
I'm sorry, what was that?
No, sorry.
I still can't quite hear you, sorry. Yeah, it's a 1 for N2 and a 3 for H2. You have to get the numbers from the balanced chemical equation. There's 3 in front of the H2 over here, and then N2, which has an implied 1. That's where you get your numbers when you're doing a mole-to-mole ratio from the balanced equation. Now that I have moles of nitrogen, now I can convert back to grams of nitrogen. Moles of nitrogen goes on the bottom, grams of nitrogen goes on the top. And for that, I'll just use the molar mass. Nitrogen's about 14, so 2 times 14, because it's N2, is going to give me about 28. 28.02 if I want to be really exact, but it's about 28. All right, there you go. That's pretty much it. Just multiply the top and divide by the bottom. What do you get? Yeah, 43. Very good. Very good. Well done. Cool. So now let's go ahead and take a look at, let's take a look at 28. How many moles of aluminum are needed to react with 2.5 moles of Fe2O3? That's 2.5 moles of Fe2O3. 2.5 moles of Fe2O3 So now you're going to go ahead and do what? How do you convert this to moles of AL? What goes in the bottom? What goes in the bottom?
Could you just put 1 mole of Fe2O3 at the bottom
Yeah.
for
How did you know? How did you know it was moles of 1 mole?
because in the equation on the reactant side, there's 1 mole of Fe2O3 for 2 moles of Al using the coefficient.
Yeah. And so what goes on top then?
2 moles aluminum.
Exactly.
Okay.
Now, just as a point of clarity, I think I would encourage always everybody to put put the units on the bottom and top first before putting the numbers. But if you actually understand the entire conversion factor in your head, you can, yeah, it's fine to put the numbers in. But otherwise, I would encourage you put the units on bottom and top first before you start putting numbers. Because starting with, if students go ahead and put numbers first, if they start putting numbers in first, I found that in many cases that causes them to make mistakes and they accidentally mess up where they otherwise would not. But yeah, in this case, this is absolutely correct. Very good. And this is a very simple problem. It's just a one-step problem. So just 5.0 moles of Al. 5.0 moles of Al is your answer, or C. Very good. Now, what do you think? Do you want to do some more conversion ones? What do you think?
29, please.
29? Okay. So let's go ahead and balance this. How do you balance this? I'll give you a second to balance it actually, or I'll give you a quick minute to balance it because I know that you guys understand how to balance these things pretty well. Once you have an answer, go ahead and raise your hand.
I got 2K plus O2, and then 2K2O.
Okay, that's very close. Very close. So let's look at this. 2K plus O2 gives you 2K2O. You are correct that that's balanced with regards to oxygen, but is it balanced with regards to potassium?
4K.
So then K would be 4.
Yeah.
4K.
Very good. Very good. Yeah, K is 4. You got it. That's an easy one to overlook. Very good. So that is our balanced equation. So now we can go ahead and proceed to do the calculation. So how would I start this? I have a 4.0 grams of potassium to start. What would I do? What would I do here? Well, first of all, let's think about what goes on the bottom. What unit goes on the bottom of this first conversion factor? Grams of K. Very good. Because the grams of K has to cancel out. And what can I convert grams of K into? What unit would go on top? Moles of O2? A good idea, but the problem is I don't know, I can't convert grams of K to moles of O2 directly. The only way to change the substance is with a mole to mole ratio. So what do I have to convert, what do I have to put on top then? Moles of K, very good. So 1 mole of K is equal to 39.10 grams of K. That's the periodic table molar mass. And what unit goes on the bottom of the next conversion factor? Yeah, moles of K, very good. And then what unit goes on the top of the next conversion factor? What unit goes on top? What am I trying to convert to?
Ram.
Can I go
Ram.
from moles of K to grams of KO2 or K2O?
Something is so confusing for me. God help me.
Remember, the only way to get from one substance to a different substance is a mole to mole ratio. So what unit has to go on the top then? What do you think? Close. I'm not actually looking for moles of O2 here. Or I'm not actually looking for O2 here. I'm actually looking for the grams of
K2O.
K2O.
K2O, yeah.
So,
Wow.
so it should be the moles of K2O that goes up here because that's what I'm looking for. Very good. And then what numbers go in front of the moles of K2O and the moles of K? What numbers
Mole
go
of K
here and
is
here?
4. Mole
Yeah,
of K is 4.
moles of K is 4 and moles of K2O is 2. Very good. All right, so now for the next one. What unit goes on the bottom of this next conversion factor?
Mole K2O.
Moles of K2O. And what's going to go on top? What am I going to convert to?
K.
Grams, yeah, grams, absolutely. Grams of K2O. So now I'm going to go ahead and calculate this. What does that give me? Moles of K2O to grams of K2O.
On the periodic table, K2O in periodic table will be
Okay.
39.10 plus K times 2 plus
Uh-huh.
O is 16. So 3.39.
Did you get
94.2.
94.20?
94.2, yeah.
Cool. So now you just multiply everything on top and divide by the bottom. What is that going to give you?
4 times 2 times 94.0 is equal to 753.6 divided
Oh,
by.
good question. Good question, Sadie. So the um oh, good, also a good question. Okay, so let's go ahead and do this. So the reason we know that the moles on top and the bottom here are 4 and 2 is because that is what is in the balanced equation. There's 2 K2O for every 4 K, which is why we have to balance it before we do the problem. The mole to mole ratio is always from the coefficients from the balanced equation. As far as the other question, as to how you get the K2O, molar mass is 94.2. That's basically this. There's 2 potassiums. Each potassium is 39.10. And because it's 39.10, if I multiply it by 2, that gives me 78.2. And then I have one oxygen. So 1 times 16, of course, gives me 16. And then I add those together, that gives me 94.20. Cool, does that make sense? Cool. Awesome. Okay. So
The answer is 4.8.
4.8, yeah. If you multiply the top, everything on top and divide by everything on bottom, you should get an answer of 4.8 grams of K2O. So just kind of a little bit of a summary of how these conversions work. I want to show you something real quick. I think it might give you a little bit of clarity on some of this stuff. So essentially, when you have moles of a substance, I'll just call it moles of A, you can do a lot of different things with it. Moles of A you can either convert to um, grams of A, which is, basically grams of the same substance, okay? And the way you convert from grams to moles is using the molar mass. And actually, let me go ahead and use a different color for the conversion factors. I'll go ahead and use this one, or this one rather. So this is a molar mass. Okay. Um, Another thing you can do is once you have moles, you can actually convert to something else. You can actually convert to molecules of A. And the conversion factor there would be Avogadro's number. You can also convert to liters of gas using the molar volume from the gas laws chapter, which is 1 mole is
Okay,
equal to 22.4 liters.
molecules or atoms. Grams, no.
Yeah, exactly. Molecules or atoms. I should make 4 atoms.
I didn't realize my microphone was on. I think I'm always jumping to use the Avogadro's number, and I just needed to see, like, no, unless they're asking for molecules or atoms, stop trying to use that number.
Exactly. And if you have moles, you can also convert to moles of something else, moles of B. And then if you have moles of B, that's where you can also convert back to grams of B. All right. So here's the thing. To go from moles to molecules or atoms, that's where we use Avogadro's number. Avogadro. Avogadro. Which is basically 1 mole equals 6.02 times 10 to the 23rd. All right. And the molar volume, this is just 1 mole equals 22.4 liters. This is something you probably learned in the gas laws chapter. I don't know if you all got into the gas laws chapter or if that's going to be on your test, but if it is, that's also something you probably have to know. And on the other side, the mole ratio, this is from the You get this from the coefficients of the balanced equation. Not sure if I spelled this right. Coefficients of, I think it was maybe supposed to be 2f's. Oh well, coefficients from balanced equation. And then as far as grams of B to moles of B, that's just the molar mass once again. But in this case, it's the molar mass of B. Does that make sense? So the key thing to keep in mind is that this moles is kind of like a central hub. From moles, you can go anywhere. If you
So
have
when you're
grams, there's really only one thing you can do: convert to moles. If you have moles, you can convert back to grams if you wanted to, but you can also convert to atoms or molecules, or you can convert to liters of a gas, or you could convert to moles of something else with the balanced equation, or and then from there you can also convert to grams of B. Oh, cool. I'm glad that helps.
So if they tell
Uh,
you to convert from mole to grams, you have to use your periodic table. You get the molar mass and everything to sort that out.
exactly.
But if
Molar
they
mass
ask you
in the
to
periodic table.
convert
Yep.
from mole to mole, convert from mole to mole, you use Avogadro, right?
Hmm.
Then if they tell you to convert from grams to mole, what do you use? You use molar mass also.
Yeah. Anytime you're going from grams to moles or moles to grams, you use molar mass, which means you have to go to the periodic table.
Okay. But if they ask you to convert from mole to mole, then you have to use Avogadro.
Yeah, well, if you go from moles to molecules, then you use Avogadro's number, or moles to atoms, then you use Avogadro's number. But if you're going from moles of one thing to moles of something else, then you have to use the balanced equation.
You have to balance the equation first before you start anything. Okay, no,
Well,
you have to use the equation they give to you.
yeah, exactly.
Oh, get you.
Yeah. So, like in this case, for example, with the problem that we were just doing, I'll actually zoom out just a little bit so we can see it a little bit better. I'll go to 100%. For the problem that we just did, we were starting with grams of K. We were starting with grams of K, and we were asked to go to grams of KO2. In other words, we were going from grams of B, or grams of A to grams of B. In order to get there, we needed to convert the grams to moles, then the moles to moles, then the moles back to grams. Does that make sense? Each one of those double arrows is one of our conversion factors. Cool?
Okay, I think I got it now. What I wrote was that from mole to mole, you use the balanced equation. From
Exactly.
mole to gram or gram to mole, you use the periodic table, which is molar mass. Then
Exactly.
from mole to molecules or atom, you use the Avogadro.
You got it.
Okay.
Very good. Very good. And yeah, and interestingly enough, in the previous problem, I was just going from moles. I was just going from moles of Fe2O3 to moles of aluminum. In that case, it was just a mole to mole conversion. I was just converting moles of one thing to moles of another. And so it was a simple one-step conversion. I just had to do that. And with the problem above there, or with the one that was way up here, can't remember what it was, number 23, I was going from molecules to grams. To go from molecules to grams, I had to start with Avogadro's number, and then I could convert the moles of back to grams. So for that problem number 20, I basically did this. I basically jumped around and converted the molecules to moles, and then I converted the moles to grams using the molar mass. All right, cool. So what would you like to cover now? We don't have a whole lot of time, but would you like to take a look at gas laws at all, or what would you like to look at? I can also do more stoichiometry. I don't know if you have any questions on energy in the upcoming exam.
We don't have gas in our exam. We've not done
You
gas.
don't have gas laws? Okay.
No, we've not done that yet.
Okay. What about energy and things like that? Did you do anything like that? Well, how about I just open it up like this? Are there any questions of any type, or is there any concept you want me to go over during this last 19 minutes or so of the session? I'm willing to cover anything, any questions you have over any topic.
For me, it's more of balancing equations. I don't really know it. That's just the reaction. 40 says the reaction shown in the above label diagram can be best described as. They've taught us endothermic and exothermic.
Oh, so you did learn that.
Yeah, we've done that.
Okay. Um, so yeah, like so for example, in this case, if you start out, so the energy increases as you go up. If you start at a higher energy, uh, let me draw, darn you. Okay. Energy is going up as you go. Energy is increasing as you go up. So you start at a higher energy and you end up at a lower energy. So going from a higher energy A to a lower energy at B, that means that you've lost energy. The reaction has lost energy. So the energy or the reactants have lost energy and now are lower energy products. A reaction that loses energy releases that energy as heat, and therefore that would be considered an exothermic reaction. And so in this case, which of the best describes A? Well, A is just going to be, this is just the energy of the reactants. That's just the energy of the reactants. So that would be this. Now, as far as it says, which of the following best describes B? This top part here, this is the, sometimes referred to as the activated complex. It's the highest energy point in the reaction. When reactants are going from reactants to products, it requires a little bit of an input of energy to get it to go. It's like trying to pop a balloon. It doesn't just pop on its own. You have to really you have to put some energy into it before it'll actually pop. But same thing with reactions. You have to put some energy into it to get it to reach that high energy state before it's into new products. Exactly. So this difference in energy from the point where you start, the reactant energy, to the point of the activated complex, this is referred to as what? This is referred to as the activation energy. Energy. Does that make sense? Yeah, there's a lot of background noise thinking. All right, that's better. All right, so activation energy. Now, so that means that B would definitely be the activation energy for the question. In the above labeled diagram, what is B? It's the activation energy. And then what is C? Well, C is the difference between the reactant energy and the product energy. So that would be your heat of reaction. This is sometimes referred to as the heat of reaction or the enthalpy. In other words, how much heat is gained or lost, or how much energy is gained or lost by the reactant. So this is going to be the heat of reaction, A. And then as we described before, the reaction showed can best be classified as what? All these other ones are really not, you couldn't really tell if it's an oxidation reaction, reduction reaction, or a decomposition reaction just by looking at it. So these are not valid. A catalyzed reaction, yeah, that also would be a little bit hard to tell just by looking at it. It really leaves you with two viable answer choices, endothermic versus exothermic. And if your energy goes down, that means heat is released, which means it's an exothermic reaction. Exo means outside, thermic means heat. Heat on the outside, exothermic. Endo means inside, and thermic means heat. So endothermic means heat is on the inside. So in other words, the reactants take in the heat and end up having a higher energy. If you want to know what an endothermic diagram would look like, it would look something like this. You basically start with energy down here, and then it would stop like right here. So the reactants would have lower energy than the products. Therefore, you would see that there's an increase in the amount of energy. In other words, energy is absorbed. So this would be endothermic. Just for anybody who wants to see that. Right. What else can I go over with you? So got 12 minutes. What can I? Any other questions I can help you with? Any other concepts you have? And it doesn't have to be from this practice test. It can be from any test, or any practice, or any homework, or just anything off the top of your head. If you give me a topic, I can come up with a question. 59. Okay. If I look at 59, scroll down. Here we go. The number of joules needed to raise the temperature of 32 grams of water from 12 degrees to 54 degrees is what? Okay, so this is anytime you have heat being added to a substance and temperature raising, chances are you're going to be using the specific heat equation, which is Q is equal to mc delta T. M times C times delta T. In your book, it may also be labeled. It may also be given as heat is equal to the mass, or M, times specific heat, which they sometimes label as SH, times the change in temperature, which is delta T. I've seen this in books as well. It means the same thing. Q is just the symbol for heat. C is just the symbol for specific heat capacity, or specific heat for short. In this case, I'm looking for the joules, and joules are a unit of heat. So essentially, I'm looking for this. I'm looking for Q, or the heat. I'm given the mass, that's the 32 grams, right? So the heat is equal to the mass, which is 32 grams, times the specific heat, which is given as 4.184 joules per gram degrees Celsius. Now the temperature change is probably the trickiest part here. How do I find the temperature change? What do I put for delta T?
The temperature change, you minus 54 from 12.
Yeah, well, yeah, it's going to be final minus initial, and the final is 54. So the final temperature is 54, that's the final temperature, minus the initial temperature, which is 12. That's going to give you your change. Anytime you see that delta sign or that little triangle, it means change. It's always final minus initial. So final minus initial. And you'll notice that if you look at the units here, the specific heat or the units of grams cancel out here, and the unit of degrees Celsius cancels out here. So I'm left with the joules, which is what I'm looking for. That's what I want. So it's 32 times 4.184 joules, because all the other units canceled out, times 54 minus 12, which is 42. And what does that give you? B. Yep. The full answer, I think, is 5,623, but rounded to the appropriate number of sig figs, which would be 2, because your 32 only has 2 and your 42 only has 2 sig figs. This ends up giving you 5,600. So very good. Very good. Excellent. Any other questions? What would you like to take a look at next?
Number 4.
Number 4. Now, I'm happy to actually go back and go over some more balancing stuff with you later, but just because we've already spent quite a bit of time on balancing equations, let me open it up to anything else people might have questions on that we haven't covered yet, just because I want to cover as many topics as possible.
Okay. For us, the kilocalories and joules and all of that was what we did in exam 1. So we're done with that one.
Oh, okay.
Yeah.
Is there any other questions that anybody has? I know some of you are probably having the gas laws. Um,
These are all exam 1 questions we did then.
okay. Well, I guess I can. You're doing gas laws. Okay, let's hit a gas laws problem at least, and then so some of these earlier ones are just like definition based ones. So I would encourage you to kind of look over those because your professor will probably include a significant number of definition based questions. So don't get too overly focused on calculation questions. But I do want to show you how to do a calculation question because I think it is important. Um, so let's take a look at some calculation-based questions. Let's do it number 83. Why not? Well, actually, that's an ideal gas law one. Oh no, it's not. It says a balloon contains which contains 0.250 moles of gas and has a volume of 11.2 liters and a pressure of 380 millimeters of mercury. What will the volume be if the pressure is increased to 1.5 atm? So this is a tricky question because there's a lot of extra information given, and not a lot of it. You don't actually need a lot of it. So the standard, the combined gas law, which really contains pretty much almost all the other gas laws, is P1 V1. And so I'm looking at 83 now, by the way. P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. So here's the question that I have for you. If is there anything here that remains constant? In other words, is there anything here that's not changing? And I've kind of read some context clues here to see it. For problem number 83, what's not changing? What's not changing here? Temperature is not changing. Yep. It doesn't mention temperature. We can take out temperature. So, is there anything else that is not changing? Don't be tricked. I'm trying to trick you here. What else is not changing? There's one other thing that's not changing. Here's a hint. Is the balloon opened at any point? Does it talk about any gas going in and out? No. So if there's no gas going into the balloon and there's no gas coming out of the balloon, what's staying the same? Not the volume. The amount. Exactly. It's the number of moles. It's a little tricky because it tells you the number of moles, but it doesn't say the number of moles changes. All it says is that there's 0.250 moles of gas in the balloon and the pressure has changed. So it turns out this is Boyle's law. P1, V1 is equal to P2, V2. What I recommend is listing out your variables, and that's what I like to do. So I list out my P1, that's my initial pressure, and V1, my initial volume. P2 is my final pressure, and P2 is my final, or V2 is my final volume. So what's my initial pressure? What's the starting pressure of this balloon? 380 millimeters of mercury. Now the truth is, it's not that it necessarily has to be like starting pressure and ending pressure, because the truth of the matter is, as long as P1 and V1 correspond to each other, it doesn't matter if they're the initial or the final, but P1 and V1 have to refer to the same set of conditions. So it says the balloon starts out with 11.2 liters at a pressure, it has a pressure of 380 millimeters of mercury. So that means that volume and that pressure go together, 11.2. Now, what does it give me for pressure 2? Yeah, gives me 1.5 ATM. Units are important here, especially because what do you notice about these units? Yeah, the units are not the same, are they? Can I solve this problem with the units as they are? With them being not the same? No, you have to convert. Now I can either convert millimeters of mercury to ATM, or I can convert ATM to millimeters of mercury. It doesn't matter which one I do. But let's say I go ahead and convert the millimeters of mercury to ATM, okay? So millimeters of mercury has to come down on the bottom, and I convert to ATM, which goes on top. And it tells me over here that 1 ATM is equal to 760 millimeters of mercury. So 1 ATM is equal to 760. I don't know if that'll be given to you by your professor, but if it's not, that means you have to memorize it. All right, so I divide 380 by 760, and if you calculate that properly, you should get 0.500 ATM. Does that make sense? All right, cool. Now that I have the pressures and the volume the same, now I can go ahead and I can uh, plug it into the equation. So P1 is equal to 0.500 ATM, and V1, of course, is 11.2 liters. And then P2 is going to be my 1.5 ATM. So now I just have to solve for what V2 is. And algebraically, that means I just have to divide both sides by 1.5 ATM. And what does that give me? What does that give me for V2? There you go. Excellent. 3.73 liters. Very good. Now what about, it says determine the volume of 0.350 moles of oxygen at STP. So here's the thing. Remember we talked about that molar volume thing earlier? Well, the molar volume is only valid at STP. So only at STP, which is standard temperature and pressure, 1 mole of any gas is equal to 22.4 liters. And standard temperature and pressure is 0 degrees Celsius and 1 ATM. Standard temperature, standard pressure. Okay, so now we can go ahead and just use the molar volume, because it is at STP, and convert the moles to liters. This is actually a pretty easy problem, but like I said, it requires you to know the molar volume. And this is certainly a problem that would be fair game for a test. So moles of O2 has to come on the bottom, and then liters of O2 can go on top. 1 mole is equal to 22.4 liters. And that should give you what? What does that give you? 7.84, yep. That's a pretty easy one. 85 is a little bit complicated. I don't expect that you would get that. 86 likewise is a bit complicated. I don't expect you'd get something like that. You could potentially if your professor was particularly mean, but I don't think you would get it. Yeah, let's do this one. Let's do 87. And at that, 87 might be our last one. I think that might be the best one to stop at. But this is a good one to definitely do. I wanted to do this one with you. Okay, so it says an anesthesiologist administered the gas at 20 degrees Celsius into a patient's body. So it's 37 degrees Celsius. What is the change in volume of 1.2 liter sample of gas as it goes from room temperature to body temperature? Okay, so using our master equation, P1 V1 is over N1 T1 is equal to P2 V2 over N2 T2. What's staying constant? What's not changing? In this case. question 87, what's not changing? Actually, volume is changing. It says, what is the change in volume? We're actually looking for the change in volume. But what's not changing? Amount. The amount is not changing. It doesn't mention anything about the amount, so you can assume that's not changing. What else is not changing, or does it not mention anything about? Pressure. Very good. It doesn't say anything about pressure. There's no ATM, millimeters of mercury. It doesn't say anything about pressure. So we have Charles' law then, which is V1 over T1 is equal to V2 over T2. So I'm going to go ahead and list my variables V1, T1, V2, T2. So what is the initial volume? What is the initial volume? So this is not totally obvious here. But yeah, it is the 1.20. And what's the initial temperature that corresponds to that volume? Yeah, it's 20 degrees Celsius. Well, no, actually, it's not 37. This is because a 1.2 liter sample. This says what is the change in volume of a 1.2 liter sample of gases that goes from room temperature. So there's the implication that the 1.20 liters starts at room temperature. And room temperature is what temperature? 20 degrees or 37? 20. So the 20 degrees Celsius is what goes here. And what about the volume? The final volume is what I'm looking for, actually. Kind of. And what is the final temperature? 37. Yep, body temperature. Now here's the thing. I cannot, I can't actually use Celsius for any of these gas laws. I'm going to have to convert each of these Celsius temperatures to what? Kelvin. So that means I'm going to have to add 273. And so 37 plus 273, this is going to give me 310. And 20 plus 273, this is going to give me 293. All right. So now that I have my temperatures in Kelvin, I can use the equation. But this equation algebraically is a little bit tough to deal with because it's fraction. You got fractions here. I'm not a huge fan of dealing with fractions. I'm sure you aren't either. So what you may want to do here is go ahead and cross multiply these just to go ahead and get started. Anytime I have one of these fractional equations like this, sometimes it's easy to just cross multiply them, and that makes it easier to work with. So the new cross multiplied equation is V1 times T2 is equal to V2 times T1. Okay? So now all I have to do is plug in the information and solve for the variable I'm looking for. I'm looking for V2. And since I'm looking for V2, I can actually just go ahead and divide both sides by T1 to get V2 by itself. And so that gives me the equation V2 is equal to V1 times T2 over T1. And now I can just go ahead and plug in my numbers. V1 is 1.20 liters. And T2 is 310 Kelvin. And T1 is 293 Kelvin. If I multiply everything on top and divide by everything on bottom, what do I get for my final answer here? What do you get for your final answer? 1.27. Yep. So 1.27. And that's liters, because Kelvin cancels out. Now the only evil thing about this is that's not actually your final answer, because it doesn't actually ask for what is the final volume. It asks for what is the change in volume. What is the change in volume? So to get the change in volume, I have to subtract 1.20 from 1.27. Yep. And that gives you 0.07. That's kind of an evil question, but now you have some tricks in how to deal with things, and make sure you read your questions carefully, and I wish you all the very best on your upcoming exam. Thank you so much for coming.